We already determined the internal energy of real gases in the von der Waals approximation, and now we derive the entropy of a von der Waals gas. When we determine the entropy of an ideal gas, we considered a given amount of gas enclosed in a cylinder with a piston absorbing the infinitesimal amount of heat dq rev from its surroundings at the temperature T in a reversible change of state. In such a process, the gas will expand and moves the piston, doing some infinitesimal work dw' on it. We follow the same procedure with a real gas in the von der Waals approximation, but first we consider a special case where the position of the piston is fixed, that is, the volume of the gas is constant and no pressure volume work is done. Then the second law of thermodynamics tells us that the infinitesimal change in the entropy S of the gas absorbing the infinitesimal amount of heat in a reversible process is equal to the ratio of dq rev to the temperature T of the gas. For a constant volume of the gas, that is for isochoric processes, the infinitesimal change of the heat can be written as the mass m of the gas, times the specific heat capacity Cv of the gas at constant volume, times the infinitesimal change in its temperature T. If we formally divide this equation by dt, then we can write the partial derivative of the entropy S with respect to the temperature T at a constant volume V as the mass m times the specific heat capacity Cv at constant volume over the temperature T. In the general case, the gas absorbing the infinitesimal amount of heat is allowed to expand and perform work on the moving piston. Then the entropy of the gas in the cylinder can be written as a function of its temperature T, its volume V, and its number of particles N. As a result, the differential of the entropy S of the given amount of gas can be expressed by its partial derivative with respect to the temperature T at a constant volume V times the differential of the temperature T, plus its partial derivative with respect to the volume V at a constant temperature T times the differential of the volume V. Here the mass m, or equivalently the number of particles N of the gas, is constant. This equation shows that the change of state of the gas in the general case can be split into two processes if we are interested in the change of the entropy of the gas. Because entropy is a state function, it only depends on the initial and the final states of the gas but is independent of the path along which the system is brought from its initial state to its final state. This situation is illustrated in the temperature versus volume diagram of the expanding gas, where the point A represents the initial state of the gas at the initial temperature T1 and the initial volume V1. The final state of the gas is represented by the point B at the final temperature T2 and the final volume V2. If we want to determine the change in the entropy, we can fix the position of the piston and heat the gas so that its temperature can reach the temperature T2 at the state represented by the point C at the initial volume V1. That is, we increase the temperature of the gas in an isochoric process between the states A and C. Then we allow the piston to move such that the warm gas could perform an isothermal expansion between the state C and its final state B, where the volume of the gas is given by V2. The two terms in the right-hand side of the infinitesimal change in the entropy S represent the two processes between the states A and C, and between the states C and B in the diagram. The first term describes the isochoric process, where we already determined the partial derivative of the entropy with respect to the temperature at constant volume. The second term in the right-hand side describes the isothermal process, where we use Maxwell relations to express the partial derivative of the entropy in terms of the partial derivative of a state variable of the gas. By selecting the position of the entropy S at the top left corner of the thermodynamic square, we need to rotate clockwise to the position of the volume V to obtain the independent variable of the partial derivative, and a further clockwise rotation gives the temperature T as the variable held constant in the partial derivative. Thus we have reproduced the partial derivative that we need to express in another form. If we start from the position of the entropy S again but rotate it counterclockwise, we arrive at the position of the pressure P as a dependent variable of the partial derivative. Then we take the partial derivative of the pressure with respect to the temperature T as a further counterclockwise rotation shows. The last counterclockwise rotation selects the volume V as the variable held constant in the partial derivative. Because both the entropy S and the pressure P appear with a negative sign in the thermodynamic square, the partial derivative of the entropy S with respect to the volume V at a constant temperature T is equal to the partial derivative of the pressure P with respect to the temperature T at a constant volume V. Now we use this result for the partial derivative in the second term in the right-hand side in the differential of the entropy. The pressure of a von der Waals gas is equal to the gas constant R times the temperature T, over the difference between the molar volume Vm and the volume correction constant V, minus the pressure correction constant A over the square of Vm. By substituting the pressure P into the right-hand side of the first equation and calculating its partial derivative with respect to T at constant volume, we obtain the ratio of the gas constant R to the difference between the molar volume Vm and the constant B. If we multiply both the numerator and the denominator by the amount of species n, Then we can write the right-hand side as n times r over the difference between the volume V and n times B. Here the product of the amount of species n and the gas constant r is equal to the mass m of the gas times its specific gas constant Rs. Now we substitute the expressions obtained for the partial derivatives in the right-hand side of the equation describing the differential of the entropy, and write the infinitesimal change in the entropy of a real gas in the von der Waals approximation as the mass m of the gas times the sum of two terms. The first one is equal to the specific heat capacity Cv of the gas at constant volume over the temperature T of the gas times the differential of T, and the second term is given by the specific gas constant Rs of the gas over the difference between its volume V and its amount of species n times the volume correction constant B of the gas, times the differential of V. In order to determine the change in the entropy of a von der Waals gas brought from the initial thermodynamic state A to the final thermodynamic state B, we need to integrate the differential of the entropy S between the states A and B. As the figure shows, we express ds in a form where the system is brought from the state A and the state C along an isochoric path, and then it is brought from the state C to the B along an isothermal path. In the first term we therefore integrate 1 over the temperature T of the gas along the isochoric path between the initial temperature T1 and the final temperature T2, and in the second term we integrate 1 over the difference between the volume V of the gas and the amount of species n times the volume correction constant B along the isothermal path between the initial volume V1 and the final volume V2. If we choose the initial state A as a zero state, where the entropy S of the system is equal to S not normally set to zero, then the integration gives the entropy S of the gas in its final state B with respect to the reference or the zero state. Let us denote the temperature and the volume of the gas in the zero state by T0 and V0 instead of T1 and V1. We can also drop the index 2 from the temperature and the volume in the final state. By performing the integrations and applying theses notations, we can write the entropy S of a von der Waals gas enclosed in the volume V at the temperature T as the sum of the entropy S0 and the mass m of the gas times the sum of the following terms. The first term is given by the specific heat capacity Cv of the gas at constant volume times the natural logarithm of the ratio of the temperature T to the reference temperature T0 in the zero state A, whereas the second term is equal to the specific gas constant Rs of the gas times the natural logarithm of the ratio of the difference between the volume V times and the amount of species n times the volume correction constant B, to the difference between the reference volume V0 and the zero state A and n times B. If we compare this expression with the one derived for an ideal gas, then we see that they differ in the correction terms n times B applied to the volume of the gas and the reference volume. We can also determine the free energy F of a von der Waals gas defined by its internal energy U minus the product of its temperature T and its entropy S. We already calculated the internal energy of a real gas in such an approximation, and found that it is equal to the mass m of the gas times the difference between the specific heat capacity Cv of the gas at constant volume times the temperature T of the gas, and A' over the square of the specific volume V of the gas, where A' denotes the ratio of the pressure correction constant A of the gas over the square of the molar mass m sub m of the gas. The specific volume of the gas is just the ratio of its volume to its mass. By substituting this equation and the expression obtained for the entropy into the definition of the free energy, we can write F as the mass m times the quantity of Cv times T, minus Cv times T times the natural logarithm of T over T0, plus A' over the specific volume V, minus Rs times T times the natural logarithm of the ratio of the difference between the specific volume V and B', to the difference between the specific reference volume V0 and B'. Here B' denotes the volume correction constant B of the gas over the molar mass m sub m of the gas. A comparison with the free energy of an ideal gas shows that the free energy of a real gas in the von der Waals approximation has the correction constant B' for the specific volumes V and V0, and the extra term A' over the specific volume V due to the pressure correction term in the equation of state of the gas. Now we consider an isentropic change of state in the case of a von der Waals gas, that is where the entropy of the gas is constant during the thermodynamic process, or in other words, the change in the entropy of the gas brought from the initial state A to the state B vanishes. Then the terms in the parentheses in the expression derived for the entropy must vanish, where the first term in the right-hand side can be written as the natural logarithm of the ratio of T to T0 raised to the power Cv, and the second term is given by the natural logarithm of the ratio of the difference between V and n times B to the difference between V0 and n times B, raised to the power Rs. This sum is equal to the natural logarithm of T to Cv times the difference between V and n times B to Rs, over T0 to Cv times the difference between V0 and n times B to Rs. Because this expression must vanish, that is the fraction is equal to 1, we obtain an equation stating that T0 to Cv times the difference between V0 and N times B to Rs is given by T to Cv times the difference between V and N times B to Rs. Here the reference temperature T0 and the reference volume V0 are constants given in the zero state of the system, that is the right-hand side of the equation is constant for any temperature and volume of the gas. Then we conclude that in an adiabatic change of state of real gases, that is in reversible processes without entropy production, we can state that the temperature T of the gas times the difference between its volume V and its amount of species N times its volume correction constant B, raised to the ratio of the specific gas constant Rs of the gas to its specific heat capacity Cv at constant volume, is constant. We note that this formula reduces to the one obtained for an ideal gas if we set the volume correction constant B of the von der Waals approximation to 0. Indeed, we already derived the condition of the constancy of the product of the temperature T of an ideal gas and its volume V raised to the power gamma minus 1. Here gamma is the adiabatic index of the gas given by the ratio of its specific heat capacity Cp at constant pressure to its specific heat capacity Cv at constant volume. That is, the exponent of the volume V is equal to the difference between Cp and Cv, over Cv. For an ideal gas we can use Meyer's relation stating that the specific gas constant Rs of the gas is equal to the difference between its specific heat capacities at constant pressure and volume. This is the expression shown above for vanishing B in the ideal gas approximation, which is constant, as expected. In order to describe the deviation of the behavior of real gases from the prediction of the ideal gas law, we introduce the compressibility factor of the gas by modifying the equation of state of an ideal gas. Now we define another quantity called fugacity, introducing similar modifications in the equations derived for an ideal gas, which gives a better description for the real case. We start with the infinitesimal change in the free enthalpy or the Gibbs potential G of a thermodynamic system given by minus its entropy S times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. For an isothermal process in a given amount of gas, the first term in the right-hand side vanishes and the infinitesimal change in the free enthalpy reduces to the expression of the product of the volume V and the differential of the pressure P. If we divide this equation by the amount of species N of the gas, we can write the differential of the molar free enthalpy Gm as the molar volume V of the gas M times the differential of the pressure P. We consider the isothermal change of state of an ideal gas between the state A at the pressure P1 and the state B at the pressure P2, where the ideal gas law states that the pressure P of the gas times its molar volume Vm is equal to the gas constant R times the temperature T of the gas. Then the change in the molar free enthalpy Gm of the gas in this process is given by the integral of the molar volume Vm of the gas with respect to the pressure P from the initial pressure P1 to the final pressure P2. By substituting the ideal gas law into the integral, we can write the right-hand side of the equation as R times T, times the integral of 1 over P with respect to P from P1 to P2. If we perform the integration, then the difference in the molar Gibbs potential between the final state B and the initial state A can be expressed by R times T times the natural logarithm of the ratio of P2 to P1. As in the case of entropy and free energy, the initial state A or any other state can be chosen as a reference or zero state with the reference value of G0 sub m at the pressure P0. Then the molar free enthalpy Gm of an ideal gas at the temperature T and the pressure P is given by the reference value of G0 sub m plus the gas constant R times the temperature T, times the natural logarithm of the ratio of the pressure P to the reference pressure P0. The deviation of the behavior of a real gas from the ideal gas law with respect to the molar Gibbs potential of the gas can be described and measured by introducing a new quantity F instead of the pressure P of the gas called the fugacity of the real gas. The fugacity F is the effective pressure of the gas, which gives the measured value of the free enthalpy G or the molar free enthalpy Gm of a real gas. We note that fugacity can also be introduced by using the chemical potential of the gas instead of its molar free enthalpy, since the multiplication factor between them is just the Avogadro constant. The relation between the effective pressure F and the measured pressure P is described by the formula stating that the fugacity F is equal to the product of a fudge factor phi and the pressure P. The multiplication factor phi is called fugacity coefficient, and it is a function of the state variables of the gas. Let us suppose that the effective pressure in the state A is described by the fugacity F1, whereas F2 denotes the fugacity of the real gas in the state B. Then the change in the molar Gibbs potential Gm of the gas brought from the state A to the state B in an isothermal process at the temperature T is given by the difference between the gas constant R times the temperature T, times the natural logarithm of the ratio of the fugacity F2 to the reference pressure P0, and R times T times the natural logarithm of the ratio of the fugacity F1 to the reference pressure P0. Here the right-hand side is equal to R times T times the natural logarithm of the ratio of F2 to F1. Now we can compare the change in the free enthalpy computed for the ideal gas law and the one measured for a real gas. For an ideal gas we can write the integral of the molar volume of an ideal gas with respect to the pressure P from the pressure P1 to the pressure P2 as R times T times the natural logarithm of the ratio of the pressure P2 to the pressure P1. In the case of a real gas the same integral of the molar volume of the real gas is given by R times T times the natural logarithm of the ratio of the fugacity F2 to the fugacity F1. We can use these expressions to integrate the difference between the molar volumes of a real gas and an ideal gas with respect to the pressure P from the pressure P1 in the state A to the pressure P2 in the state B, which can be written as the gas constant R times the temperature T, times the natural logarithm of the fugacity F2 of the real gas in the state B to the fugacity F1 of the real gas in the state A, minus R times T times the natural logarithm of the pressure P2 to the pressure P1. The right-hand side is equal to R times T times the natural logarithm of the ratio of F2 divided by P2 to F1 divided by P1, where we can express the logarithm of the fraction as 1 over R times T, times the integral of the difference between the molar volumes of a real gas and an ideal gas with respect to the pressure P from the pressure P1 to the pressure P2. Let us suppose that the pressure P1 in the initial state A tends to 0 and we can use the ideal gas approximation to describe the behavior of the real gas in its initial state. In this case the fugacity, that is the effective pressure, approaches the pressure, and the fugacity coefficient phi becomes 1, that is the ratio of the fugacity F1 to the pressure P1 in the initial state A tends to 1. Then the left-hand side of the equation is equal to the natural logarithm of the ratio of the fugacity F2 to the pressure P2, where we integrate from 0 pressure in the right-hand side. Since the fugacity F2 is equal to phi times the pressure P2, the ratio in the logarithm can be written as the fugacity coefficient phi, and we can drop the index 2 from the pressure in the final state. As a result, we have an equation that defines a quantity measuring the deviation of the behavior of a real gas from the ideal gas law with respect to its molar enthalpy in an isothermal process in terms of the difference between the molar volumes of a real and an ideal gas. Now we can apply the ideal gas law telling us that the pressure P of an ideal gas times its molar volume V sub m ideal is equal to the gas constant R times the temperature T of the gas, and the real gas law for the same pressure and temperature stating that the pressure times the molar volume V sub m real of the real gas is equal to the compressibility factor Z of the real gas times R times T. Then 1 over R times T, times the difference between V sub m real and V sub m ideal can be expressed as Z minus 1 over P, and the natural logarithm of the fugacity coefficient phi of a real gas with the compressibility factor Z at the temperature T and the pressure P, is equal to the integral of the compressibility factor Z minus 1 over the pressure P with respect to the pressure from 0 to the pressure P. Here we indicated that the compressibility factor of a real gas depends on its temperature and pressure, and if Z is a known function of the state variables then the fugacity coefficient of the gas can be derived from the integral. We already saw that the compressibility factor Z is a universal function of the reduced temperature and the reduced pressure for any real gas, and its value for given reduced temperature and reduced pressure can be determined by using generalized compressibility charts. At the same time, the differential of the pressure P over the pressure P is equal to the differential of the reduced pressure PR over the reduced pressure PR, which indicates that the fugacity coefficient expressed in terms of the reduced temperature and the reduced pressure is also universal for any real gas. Then we can plot generalized fugacity coefficient charts for real gases, for example these chart compiled for pure substances. As in the case of the compressibility charts, we can see different plots for different ranges of the reduced pressure of the substances. In the first chart the fugacity coefficient phi is plotted as a function of the reduced pressure PR from 0 to 0.5 at constant reduced temperatures between 0.5 and 1.6. In the second chart the range of the reduced pressure is between 0.1 and 50 at the constant reduced temperatures from 0.65 to 15. Here the blue curve represents the saturation line separating the phase of liquid saturated vapor from the phase of unsaturated vapor for all substances. The parts of the curves represented by dashed lines in the first chart are in the range under the saturation line. The charts show that at very low pressures the fugacity coefficient is close to 1 as the ideal gas approximation still gives a reasonable description of the behavior of real gases. In this range the effective pressure is essentially the same as the real pressure of the gas used in the calculation of its molar free enthalpy. With increasing pressure, the fugacity coefficient drops to a minimal value for a given reduced temperature, that is the effective pressure is less than the real pressure of the gas. The minimum value of phi increases with increasing reduced temperature. Above a given reduced pressure depending on the reduced temperature, the fugacity coefficient starts to increase and it will surpass 1 at some point. The higher the reduced temperature is, the less the reduced pressure at which phi becomes greater than 1. In that region the effective pressure becomes greater than the real pressure of the gas when we determine its molar Gibbs potential. We finish the discussion on the fugacity of real gases with the approximation of the fugacity coefficient of a von der Waals gas, and we also give some remarks on the enthalpy of real gases. We saw that the compressibility factor Z of a real gas can be expressed as the pressure P of the gas times its molar volume Vm over the gas constant R times the temperature T of the gas. If we substitute the von der Waals equation into the pressure in the fraction, the right-hand side becomes Vm over the difference between Vm and the volume correction constant B, minus the pressure correction constant A over R times T times Vm. Here we introduce the notations capital A for A over R squared times T squared, capital B for B over R times T, and H for B over Vm, which is similar to the conventional notations applied for the modified versions of the von der Waals equation of state. By using this notation, the compressibility factor of the von der Waals gas can be written as 1 over 1 minus H, minus capital A over capital B, times the pressure P. Although the formula obtained for Z has a simple form, we need to express the compressibility factor in terms of the pressure and the temperature in the calculation of the fugacity coefficient. If we write the molar volume Vm of a von der Waals gas as the compressibility factor Z of the gas times the gas constant R times the temperature T of the gas over its pressure P, we can use the so-called ideal gas approximation of the molar volume which we introduced in the discussion on the Joule-Thomson effect. In such an approximation the molar volume of a von der Waals gas is written as R times T over P, plus the volume correction constant B of the gas, minus the pressure correction constant A of the gas over R times T, plus A times B times P over R squared times T squared. Then the ratio of Z minus 1 to P can be approximated by 1 over R times T, times the quantity of B minus A over R times T, plus A times B times P over R squared times T squared. Here we can apply the notation introduced above, and write the right-hand side as capital B minus capital A, plus capital A times capital B times the pressure P. Because we need to integrate the left-hand side of this approximation to obtain the logarithm of the fugacity coefficient phi, we can insert its right-hand side into the integral and perform the integration. As a result, the logarithm of phi is given by the difference between capital B and capital A times the pressure P, plus capital A times capital B over 2, times the square of the pressure P. Here the second term represents a second-order contribution of the pressure in this approximation. Since we have already determined the entropy and the free enthalpy of real gases, we also derive an expression for their enthalpy. The infinitesimal change in the enthalpy H of a thermodynamic system is equal to the temperature T of the system times the differential of its entropy S, plus the volume V of the system times the differential of its pressure P. In the case of isothermal processes we can formally divide this equation by dP, and write the partial derivative of the enthalpy H with respect to the pressure P at a constant temperature T as the temperature T times the partial derivative of the entropy S with respect to P at constant temperature, plus the volume V. Here we use the Maxwell relations encoded in the thermodynamic square to cast the partial derivative in the right-hand side into a more convenient form. By selecting the position of the entropy S at the top left corner of the thermodynamic square, we need to rotate counterclockwise to the position of the pressure P to obtain the independent variable of the partial derivative, and a further counterclockwise rotation gives the temperature T as the variable held constant in the partial derivative. Thus we have reproduced the partial derivative that we need to express in another form. If we start from the position of the entropy S again but rotate it clockwise, we arrive at the position of the volume V as a dependent variable of the partial derivative. Then we take the partial derivative of the volume with respect to the temperature T as a further clockwise rotation shows. The last clockwise rotation selects the pressure P as the variable held constant in the partial derivative. Because only the entropy S is the dependent variable that appears with a negative sign in the thermodynamic square, we apply a negative sign for S, and state that minus the partial derivative of the entropy S with respect to the pressure P at a constant temperature T is given by the partial derivative of the volume V with respect to the temperature T at a constant pressure P, which can be inserted into the right-hand side of the equation. Then the differential of the enthalpy H is equal to the difference between the volume V and the temperature T times the partial derivative of V with respect to T at constant pressure, times the differential of the pressure P. This expression can be used to determine the residual enthalpy of the real gas in an isothermal process. Residual properties quantify the deviation of a real gas from the behavior of an ideal gas at the same temperature and pressure, That is, residual enthalpy is the difference between the actual enthalpy of a real gas and that of an ideal gas at the same temperature and pressure. The residual free enthalpy characterized by the fugacity of the real gas or the residual entropy can be defined in the same way. Because the molar enthalpy of a system brought from the zero state to an arbitrary thermodynamic state is given by the integral of Hm along an isothermal path between these states, the result can be substituted into this integral and we integrate the difference between the molar volume Vm and the temperature T times the partial derivative of Vm with respect to T at constant pressure. The integral is performed with respect to the pressure P from zero pressure in the zero state to the pressure P in the actual state. If we substitute this result into the definition of the residual enthalpy of a real gas, we obtain the difference of two terms in the right-hand side calculated for the real gas and the ideal gas, where n denotes the amount of species of the gas. In the first term given for the real gas, we can write the molar volume Vm in the integral as the compressibility factor Z times the gas constant R times the temperature T over the pressure P. In the second term given for the ideal gas, the compressibility factor is equal to 1. If we compute the partial derivative in the integrals, we can see that the second term vanishes and we can state that in an isothermal process the residual HR of n mole real gas at a given temperature T and pressure P is equal to minus the amount of species n times the gas constant R times T squared, times the integral of the partial derivative of the compressibility factor Z of the gas with respect to its temperature T at constant pressure times 1 over the pressure P. The integral is computed with respect to the pressure P from zero pressure to the actual pressure P of the gas. Accurate experimental data can be used in evaluating this expression, but general compressibility charts also provide the values of the compressibility factor of real gases for given reduced temperature and reduced pressure.